Hello, everyone. My name is Devjit Gopalpur, and this is Brian O'Connor. I'm from Google, Brian's from ONF. So we're here to present Stratum, which is an open source project that is helping to enable the next generation SDN to enable some of the open and programmable devices. So as we look into the next generation, we just want to take a moment to just to take a quick peek at the rearview mirror. So Google's SDN network. So Google is in the second decade of running SDN networks. We've had tremendous success at various topologies. The very first truly SDN fabric is called B4. This came out about nearly 10 years ago. And this connects the inter-data center. It carries the inter-data center traffic, connects our geographically separated data centers, and the demand for capacity here is the largest. Given, based on the success of B4, we moved on to converting our data center fabric to Jupyter. It's called Watchtower, moved to Jupyter. And this has, again, proved to be a huge success for us to sort of deploy newer topologies and enable new applications and workloads. Many of the workloads that you might have heard about in talks in the last couple of days applied directly to many of the things that we run on Jupyter. We took that success and applied it to the peering fabric that we use, that we call Espresso. This is where we peer with the ISPs and the network that the internal at Google is called B2, and we started, we introduced the SDN control plane for the peering for the metro fabric, and this is called Espresso. And so as we grow, add capacity, we want to have a means of flexible control for ease of manageability, and we are looking to evolve our SDN solution to use some of the new paradigms, and which we're going to talk about in the rest of this talk. Quick look at how ONF has evolved. ONF started off with the OpenFlow 1.0 solution, again, about 10 years ago, and then built the ONOS SDN controller on top of that. All of this, again, was based initially on OpenFlow, and used ONOS to sort of leverage ONOS to enable telcos and service providers to utilize their resources efficiently with CARD, and now with SEBA, which you probably heard in some of the talks earlier, which is basically SDN-enabled broadband access for residential solutions. And of course, there's the trellis, which we have, which ONF has sort of built on top of. It's a fabric that utilizes ONOS to sort of enable leaf spine fabric. And which sort of brings us to Stratum and how we can enable some of the new open hardware, programmable hardware, using what we have learned with experience from OpenFlow and other frameworks. So again, so what are the benefits we are trying to get from using an SDN-based approach. So we want fine-grained control. What that means is we want to be able to quickly react to network events and program devices and use the devices that we have in the network to quickly react. So basically reprogram the devices at runtime. This is an important point, control plane optimizations. So a disaggregated network has its advantages, and we still need protocols to sort of talk to the different control elements. A centralized control plane gives the additional advantage that you can have an overall view of the network. You can run your application centrally, and you have a centralized database where you can analyze your events, your monitoring data to quickly adapt to newer to events, as well as to when you need to deploy new applications, you have all of the data that you need centrally. And monitoring, of course, is an important aspect. One of the main pain points for DevOps, is manageability. Given a centralized centralized control plane, and hopefully an adaptive data plane would give this would give the DevOps a centralized view of the network. And the most important, or again, another important feature is adding new features. So, think about how we evolve how we, like especially in the switching world, you can go from writing new software or spinning new chips in order to achieve deploy new features. But if all of this can be done as just a software change, that gives the flexibility to operators and anybody that's running the network to sort of deploy features at basically at software timescale. So now that we have open hardware, programmable hardware, how do we evolve our SDN to adapt to this? So we provide a new control interface which will abstract out the capabilities of the different types of hardware. So you could have merchant silicon, you have white boxes, black boxes, whatever you might call it. We abstract this out using some sort of programming language or any other abstraction that you might want, and have this available to your control plane to then define the policies, to define flows, to define forwarding tables, etc. And we talked about monitoring. So now you could, so let's say if you can have a common modeling framework, and then you can use this modeling framework and a set of APIs to configure your devices, to monitor, to troubleshoot, etc. So we'll talk about that in a moment. And similarly for operations. So common operations like software upgrades, updating security certificates, etc. And we need a platform that is an operating system and an API to sort of to get all of the information from your peripheral devices, from maybe your switching ASIC, etc., to gather the fine low-level telemetry data. So we have a common platform abstraction, and we use ONLP for these, and we'll talk about that in a moment. So basically, we put all of these together, and what you get is your an open source switch stack, or a switch operating system, as you might call it. And what does it give us? Helps us define some vendor-neutral applications, control applications. So what it means is you write your network, based on your network intent, you write as a program, a control plane function, and then you compile this to different backends. So going back to the point about rollout of new features at software timescale, this is exactly what enables this this capability. And so with new programmable hardware, for example, Barefoot, Tofino, we want the hardware to be to sort of mimic exactly what our intent is, and so this new control plane sort of gives that flexibility to exactly specify what your hardware capability is defined. So you're basically pushing the hardware abstraction a level up in the stack, making it available to the control plane, and then helps you with faster deployment. And we talked about the network model. So basically, you get a uniform network model here, which again is helps. So your telemetry configuration management. And that essentially gives us something that's vendor agnostic. You can enable whitebox switches from multiple vendors and have a homogeneous view of the network. So putting it all together, all of the keywords. So you want to be able to deploy your software at scale. You want to be, and then be able to migrate services from traditional networks to from traditional devices to programmable devices, or to achieve scale, be able to dynamically change between functional blocks, and helps with this migration. And we talked about management. So you can develop common tools, and that reduces time to deploy, configure, monitor, etc. Brian?
Cool. So my name is Brian O'Connor with the ONF, and we're going to just talk quickly about some of the interfaces that Devjit is describing. So the first thing is we use P4 to define the pipeline. And it's important to note here that we use P4 for both the programmable, new ASICs or FPGAs, as well as it can be used as a contract definition language for fixed pipeline. So we have in the Stratum project an architecture we're calling the fixed pipeline model, which enables you to map P4 programs down to the ASIC resources in a more traditional sense. So the P4 program is going to be how you define or model your parser, your ingress, deparser, and egress pipelines. This is an example of the PSA architecture, but if you have a fixed pipeline from your vendor, it's going to look a little different. P4 can be still used to model it. But once you have this lower level entities that you want to access in a vendor agnostic or vendor neutral way, we need an interface to do that. And that's where P4 runtime comes in. So P4 runtime gives us programmatic control of all of the entities that you can describe in your pipeline description. Things like tables, table entries, the action profiles and groups, meters, counters, configuring the multicasting of traffic, setting and reading registers, stuff like that. So if you can model it in P4, you can control it using P4 runtime. And this goes on to provide a clear definition of the role that we are requiring from a particular device. It enables you to provide a model that works across different ASICs. So for example, if we have ASIC families, two different ASIC families from the same vendor or two different ASIC families from different vendors, we can have a simplified logical view of the pipeline for the specific role in the network. And then we can use P4 and P4 to define it and P4 runtime to control it. This enables us to write our control plane once while still giving some degree of extensibility and flexibility to the operator of the network without having to go through a standards body to get new functionality achieved. For operations administration management, we have two new interfaces that both come from the OpenConfig project. So for configuration, monitoring, and telemetry, we use GNMI. And for operations, we have GNOI, which is a set of microservices. So things that we'd want to do in common ways across vendors. On the configuration front, we'd want to update QoS, scheduling, CERDES, port channelization, configure the management network. We want to read and write peripheral state, read sensor data, and then also do some of the security and software update reboot that Devjit was alluding to. And so through these two interfaces, we're able to achieve declarative configuration through the OpenConfig Yang models. These models are common across all of the platforms that we're targeting for support under Stratum. GNMI goes a step beyond what you get out of something like netconf in that you can subscribe to events and receive streaming updates of just the deltas when there are changes that occur. And then in both of these cases, the OpenConfig models are vendor neutral, but they're extensible. You can through augmentations add additional functionality if you have additional functionality or features you need from your specific platform. So putting this all together, we have a pipeline definition for fixed function and programmable ASICs that we're doing in P4. To control that pipeline at runtime, we have a gRPC interface called P4 Runtime, which is a collaboration between Google and the P4 language consortium and many of its members. We do configuration and streaming telemetry through GNMI using the OpenConfig model set. And then for operations, we've got a set of microservices under the umbrella of GNOI. Stratum is an implementation of these interfaces that's intended to be done in a vendor, both switch vendor, ASIC vendor, and platform vendor agnostic way. But you may be asking, well, just with these interfaces, that's not a networking solution. And you can really think about Stratum as a foundation that's going to run on your devices. We call it a thin switch OS or a thin NOS because it doesn't necessarily have all the same control plane building blocks that you'd have in other solutions. If you're going to put this together into the overall SDN picture, there are going to be a set of services for doing fabric or control plane control, configuration, monitoring, telemetry, administration, and orchestration that are going to run in your compute cluster, probably in the same data center, maybe near rack or could be anywhere really. You'll have a contract for the various roles. For example, if a device is a leaf or a TOR, you might have one profile. If it's a spine, you may have another profile, which may have different or less requirements. And then we've got a common set of interfaces that will work across these boxes in a multi-vendor environment. This solution now is a complete network stack that can plug into your inventory database, global orchestrator, or traditional OSS and BSS systems. And then on the side here, we've got some of the pieces, the open source pieces or options that you can use in this. And if you think about the data plane, we've got ONL and Stratum that are providing hardware abstraction, and then the control plane and orchestration plane would be platforms like ONOS and Cord from ONF.
So a quick look at what Stratum looks like from a software perspective. It's basically a Linux process that's running in user space, with of course dependency on OpenConfig gRPC as we just mentioned. It encapsulates the runtime, the P4 runtime, GNMI, GNOI services as gRPC, and we use Bazel right now for compiling all of this together. It can be packaged with ONL, and of course for the platform APIs we use ONLP. Quick look at what the high-level architecture looks like. We mentioned that we abstract out different types of hardware. So all of this on the left-hand side you see is where the ASIC abstraction is done. The blue box here is basically the switch agent, the Stratum switch OS, and below that it talks to the ASIC specific SDK. So the Stratum agent runs the gRPC services for P4 runtime GNMI, GNOI, as you see at the top. And the switch broker interface is basically the interface that sort of has that basically exposes the or implements the services, provides the interface for the services to program your pipeline definitions and then the switch configuration. On the right-hand side is where the ONLP PHAL interface comes into the picture. You might have seen some of this in a couple of talks yesterday, by Delta and EdgeCore, this, as Brian is going to talk, has been deployed with EdgeCore and Delta. Yep.
So just jumping quickly into some of the use cases to motivate some of this. A lot of the use cases that we're targeting for Stratum fall under the umbrella of SDN. Stratum can be used as a foundation for something under some of the NOSes that you heard about for the control planes that Devjit alluded to. You can also run ONOS and Trellis on top of this, or you can do full-blown NFV SDN service delivery. We'll also just quickly throw in a traditional use case where we can show some value that Stratum can add even if you want to run your control plane on the box. So the first use case we can talk about is a one from Google. So today, and in many SDNs, you have to have a fairly homogeneous network because you have to adapt your control plane to the interfaces that you have. But once we insert a layer of common interfaces, common control and common modeling, we can start to provide a more heterogeneous solution. So we can have some platforms coming from Google. We can have other platforms like some of the TORs be whiteboxes, and then have traditional OEMs or networking vendors provide things like aggregation blocks, spines, or TORs. In this case, the flow programming is done using a common interface. The control plane is modeled using a common interface, and we can get information about the box using common models. It's important that we can continue to exploit unique hardware capabilities of these devices, and that's where the extensibility of something like P4 or the extensibility of the OpenConfig models comes in. But ultimately, in a solution like this, the goal is to leverage commercial vendor technology and not have to build or use a single vendor across an entire deployment. The next use case we'll talk about falls into that second bucket, moving from left to right across the previous slide. And this comes from Tencent. And Tencent's goal is to take their monolithic fabric, their unified fabric, and disaggregate it using off-the-shelf white box switches. For example, the line cards of your traditional solution become lead for TOR switches. The fabric card become spine switches, and then instead of having the on-the-box switch OS, you can extract that into an SDN OS that runs using these P4 runtime GNMI and GNOI cases. It's important to note from Tencent's perspective that this doesn't mean going all SDN all in together. In this case, each of these fabric pods would have its own controller. They're looking for a network of controllers that are based on some of the technologies that ONF is providing. This gives you the freedom to use different protocols or RPCs within your network, and then different ones outside. And the goal is that the SDN controller is responsible for the integration with legacy network technologies. You can then replicate this block over and over. The last use case in the SDN category we'll talk about today comes from NTT. And the goal here is to provide flexible service chaining through network functions. These could be VNFs, or they could be network functions that are on the networking devices you have. So first, traffic is steered through the network functions by the controller using P4 runtime based on a policy that comes to the controller from an external system. The goal of this solution is to automatically scale the network functions in response to load triggers. So we get back things like INT, in-band network telemetry reports, or flow and port stats from the device. When we determine that a certain network function is nearing or at capacity, we can trigger multiple instances of that function to be spun up, and then we can do things like ECMP routing across the various functions to achieve load balancing. The other thing that is part of this use case is to be able to detect things like DDoS or flow bursts, throttle and mitigate them either using functions or using queuing in the devices. And again, we're detecting that through telemetry, and then we're using traffic steering via P4 runtime. The last use case I'll talk about is potentially a design idea or potential design pattern that could be used. And that's, how can we build a traditional and programmable router using Sonic? Sonic's a project that obviously you probably are probably way more familiar with than Stratum. It's starting to gain a lot of traction adoption, and a lot of the benefits are realized by using the SAI pipeline and a set of control plane applications that have been written for SAI. So how can Stratum help here? As some of you may be aware, there's an architecture that's been written in P4 called FlexSci. It's part of the SAI project today. And on top of the FlexSci architecture, we have a definition of the SAI pipelines in P4. So if you wanted to, you could take that architecture and you could compile it down for a P4 enabled switch, either a fixed switch or a programmable switch, and then run it on a Stratum box. Obviously, we'd need to do some adaptation from the SAI layer that we have in Sonic down to Stratum, but Stratum could serve as a foundation there. But what does that enable you to do? It means that when a user comes along with a new application, instead of having to go through the SAI extension process now, which typically involves writing new header files and then mapping them into the database, the user could provide a P4 snippet for the part of the pipeline. The green pieces here are the flexible parts, the part of the pipeline that they want to augment or control. They could provide a control plane for that, and you could just load a user app as a Docker container as part of the whole Sonic ecosystem. So what we're providing here is potentially a layer of compatibility where Sonic can control the black boxes, the standard pieces that are part of the spec, but you can also start to play with data plane extensions in a way that is a little bit clumsy or difficult to do today. The next part of the talk, we'll just explore how we're working with OCP. So from an OCP software perspective, Stratum is built on ONL, Open Network Linux, and leverages ONLP as our primary platform API. Google and the rest of the Stratum community has been a contributor and driver for the next generation of ONLP called V2, which is going to be merged to master probably within the next few months. And that gives a little bit of additional functionality and semantics around the ONLP API that was in existence. And then like pretty much everyone else in the whitebox switch industry, we're using ONI to boot these images on the switches. From a hardware perspective, we're targeting two ASIC lines, the Broadcom Tomahawk, Broadcom Tomahawk line and the Barefoot Tofino line. And there's some boxes from EdgeCore and Delta that fall under the accepted, under review, or inspired category that Stratum works on today. There's a larger set of devices that fit these two families that are also supporters in the works for, and we also have ONLP support for as well. From a community perspective, we've got Google and Tencent as our lead cloud operators, and then several telcos that have use cases and are talking about potential field trials and POCs using this technology. We've got a number of switch vendors, both on the ASIC vendor side, ODM, OEM side, and a number of open source projects we're currently collaborating with. Quickly on the roadmap, we've been at this for about a year. You may have heard announcements about this time last year about the community launch. We've gone through a pioneer phase where a few early adopters have ported the source code, which Devjit didn't mention, but was originally donated by Google to some white boxes. And we're currently in a phase called the member preview, where people are trying this out, seeing if they can build out a few use cases. And we're targeting open source launch around the middle of the year. At that point, we hope to expand the set of chipsets and also work on some of the synergy with other OSs. I'll just leave this slide up. If you're looking to get involved, we certainly welcome you now or when it becomes public, and happy to take some questions if we still have time.
I have a question. All right, so I just don't know how this would work, right? So in terms of loading a P4 snippet from like a kind of global control plane sort of thing, right? How does that look? Does it go through GNOI or JNMI, or is there like custom loader that you talk to somehow?
Yeah, so there's two parts. The first part is that you write your P4 code. It needs to be compiled into something that's going to realize whether or not the P4 program is realizable on your target, and also what the mapping is down to the ASIC resources. Once that binary is produced, that can be done sort of at P4 design time. At load time or runtime, P4 runtime, that interface, in addition to writing and reading flow information and the other pieces, also has a mechanism to push a new pipeline configuration.
Okay, and like remotely over the network.
Yep. Yeah, exactly. That's the canonical way of pushing it. Is you push your pipeline over P4 runtime, and then you can start to program entities against that program.
Cool. Thanks.
Mm-hmm.
Hello. The question I have is, how flexible is Stratum around SAI?
So
in terms of, if I want to push down logic to the ASIC, I know that the SAI is a pretty fixed, kind of abstraction.
Yep.
So for Stratum is a P4 runtime and plus other interfaces. So let's say if I want to push down anything to the ASIC, but it has to go through the SAI, I wonder, the flexibility, between the two.
So one thing will maybe clarify the point. So today our integrations are directly against vendor SDKs. We don't actually use SAI as an abstraction. And that gives us additional flexibility. Basically, if the ASIC can do it, or the ASIC SDK can do it, and you can model it in P4, then we can use the full complement of functionality.
So you're just doing a one-to-one match, one-to-one mapping. Am I right?
Well, yeah. So today we use a vendor-specific compiler. We can go back to this slide. So today we're using a vendor-specific compiler and a vendor-specific SDK. And so we can basically, if the SDK can do it, then we can allow a P4 program to do it. There have been some proposals to put like SAI in place of the switch SDK, which you're right, would constrain the types of programmable things that we can do. Yep. We haven't layered it there yet. If there are some use cases that would require it, it could be done. But we haven't invested a lot of time there.
Okay.
Do you have a comment, Ali?
Essentially, we want to make sure that if there is flexibility that we can use, we are not like limited to what SAI provides. If SAI can provide that, we'll just go ahead and use it. If SAI cannot provide it, we'll just go ahead and directly use the SDK.
Yeah, I think the model that we proposed, where we use like the SAI architecture, enables you to write control planes against a common set of tables. But then you have insertion points where you can have smaller control plane pieces that just talk to specific P4 lets or sub tables, or rather than having to do. So we can get both benefits by providing the P4. Using the SciFlex architecture, we basically get SAI, but then we have the capability using the vendor SDKs to address additional functionality that you may need for your use case, which is the user.p4 piece.
Any other questions? Well, thank you all. It's been oh, one more? Yeah, okay, go.
Actually, just basic question. If I don't need to change the pipeline, I just need to use the standard capability of a chip. It's Stratum needed, or basically is Stratum specifically built for SDN and changing the pipeline, or not?
Yes.
Or is it an SDN application, or is it?
No.
So if it's not an SDN application, you can have like some fixed configuration that you always push to the switch and you keep using it.
So still we could use Stratum?
Yeah, you can have like a very simple agent running on the switch that pushes all the flows all the time that your switch comes back up. So it goes back to the traditional use case that you can actually have Stratum running as an agent underneath, and everything else just push like some set of fixed flows for you. Even a configuration could be a fixed configuration. You really don't need to use it.
So
you can just use the telemetry information if you really want to monitor your switch.
So in terms of the feature support, I don't recall I see roadmap there, like specific, like some forwarding features.
Okay, forwarding features. So do you want to talk about what features are going to be supported?
So for forwarding features, it depends upon the target. So if you're talking about some of the fixed function targets, standard L2, L3, VLAN port filtering, tunneling, and packet I/O are the basic things that we were covering today. If you're talking about the programmable ASIC family, either the FPGAs or something like the next generation programmable ASICs, whatever their compiler will support, which is pretty much any data plane header you can think about and write in a P4 program.
Okay, thanks.
So there's some degree of target specificity for support, just because, that's what we get from the APIs and the SDKs that we have. But that being said, things like GRE, MPLS, tunneling technologies that you may have support for in the SDK. We may not initially have support for them for the fixed function ASICs, but those are some of the things that our community is starting to talk about and roadmap support for.
Right. It's interesting to see. You've got the fixed function switches, the Tomahawk switches, plus the barefoot switches, and of course, great to see the use of the different OCP software, ONI, ONL, ONLP. And then even some of the exploratory, hey, what about SAI and how we can start working together? So please help me thank the speakers.